Welcome back to Plan and Manage Schedule. In earlier parts of this lesson, you learned how predictive projects estimate durations using parametric and bottom-up methods, and how adaptive teams size backlog items with story points using relative sizing. Now it is time to put those estimates into order. This part is about sequencing, deciding what happens before what. You will see how predictive projects use the precedence diagramming method to link activities with formal logical dependencies, walked through with a house-building example. Then you will see how adaptive projects sequence work differently through backlog priority and dependency analysis using a mobile banking example. By the end, you will understand how both worlds decide what comes first and why. In this part, you will see how predictive schedules link activities using formal dependency logic and how adaptive teams sequence backlog items through priority and blocking. Start with the 4 relationship types. Finish to start is the most common relationship, and the one you will see throughout the house-building example ahead. The predecessor activity must finish completely before the successor can begin. Permits and foundation must finish before framing and roofing can start. There is no overlap at all between the two. Start to start means the successor can begin as soon as the predecessor begins. The two run together rather than one waiting for the other to finish. Testing might start as soon as development starts, even though testing finishes much later. The link governs start timing, not completion. Finish to finish means the successor cannot finish until the predecessor finishes, even though both may run in parallel for most of their duration. Picture 2 teams writing documentation and finalizing code. The manual cannot be finished until the code itself is finished, though both are worked on at the same time. Start to finish is the rarest relationship you will encounter. It means the successor cannot finish until the predecessor starts, and you will mostly see it in specialized scheduling, such as a night shift that cannot end until the day shift officially begins. It exists in the method, but it appears far less often than finish to start. Notice that the house-building example you are about to walk through uses only finish to start relationships. That is intentional. It is by far the most common logical relationship in predictive scheduling and the easiest to reason about. Permits finish, then framing starts. Framing finishes, then exterior work starts. But do not let that fool you into thinking every predictive schedule is built this way. Real schedules often mix start to start and finish to finish links whenever 2 activities can genuinely run side by side. Recognizing where dependencies could overlap is exactly the kind of thinking that later compression techniques rely on. For now, just remember this. 4 relationship types exist in the method, but finish to start is the default you will see most often, both in this course and in real project schedules. Let's ground the 4 relationship types in one running example, building a simple house. Here are 6 of the 7 activities, their durations, and what each one depends on. Activity A is permits and foundation, taking 5 days. It has no predecessor. It is the very first work on this project, and everything else depends on it finishing first. Activity B is framing and roofing, taking 10 days. It depends on a finish to start link, since you cannot frame a house before the foundation and permits are complete. Activity C is exterior work, siding and windows, taking 6 days. It depends on framing and roofing. B, finishing first, since you need the frame up before attaching the exterior. Activity D is rough-in plumbing and electrical, taking 8 days. Like exterior work, it depends on framing, finishing. Notice C and D share the same predecessor, B, so they can run in parallel. Activity E is drywall and interior finishes, taking 12 days. This one depends on both C and D finishing. You cannot close the walls until exterior work, and the rough-ins are both done. Activity F is landscaping, taking 6 days. It depends only on A, the foundation, finishing, not on framing or anything after it, so it can proceed on its own timeline. Now look at the complete picture, including the 7th activity, G, final inspection, a single day. This precedence diagram shows every logical relationship at once, drawn as boxes connected by arrows, each arrow representing a finish-to-start dependency. Follow the flow from start to end. Permits and foundation, A, feeds two independent branches, framing and roofing, B, and landscaping, F, both begin once A is done. From framing, the path splits again into exterior work, C, and rough-in plumbing and electrical, D, both depend only on B, so they proceed side by side. Those two branches converge into drywall and interior finishes, E, which needs both C and D finished before it can begin. Finally, everything converges once more at G, final inspection, which cannot start until both E and F are complete. This split-then-merge pattern is exactly what a network diagram is built to show clearly. Here is the real distinction, and it is more precise than it first sounds. Both predictive and adaptive projects must respect technical dependencies. You cannot skip a step that genuinely has to come first in either world. The difference is what decides the order among items that have no such hard technical link. In predictive scheduling, that order is fixed once in the network diagram and locked into the baseline, changed only through formal change control. In adaptive scheduling, that order is continuously rederived from backlog priority, what matters most to the business right now, while dependency analysis still checks that nothing gets pulled into a sprint before its true prerequisites are ready. Priority decides the tie breaks. Dependency still governs what is physically possible. Here is what backlog priority and dependency analysis look like in practice, using a mobile banking product backlog. At the top of Sprint 1, in top-to-bottom order, sit 3 high-priority user stories, creating a unique @Zen tag, securely linking a bank account, and viewing that linked account on a profile screen. One level up, in medium priority, sits Epic 1, user profile and bank linking, which depends on those 2 stories being completed. Next to it sits Epic 2, send and request money flow, and it is explicitly blocked by Epic 1's completion. Meanwhile, low-priority ideas like AI-powered support and multi-currency support sit untouched, with no current dependencies at all. This is dependency analysis at work inside a backlog. It ensures a logical build order and prevents the team from pulling in work it is not yet ready to do. Let's trace that chain one link at a time, from the first story a developer picks up to the epic it eventually unlocks. The chain starts with creating a unique @Zen tag. This story has no dependency at all. It can be pulled into the sprint immediately, which is why it sits at the very top of the high-priority column. Next comes securely linking a bank account. The dependency rules state this depends on completion of the first story. In practice, a user needs an identity, the Zen tag, before the system links a funding source to it. Epic 1, user profile and bank linking, cannot be considered complete until both the Zen tag story and the bank linking story are finished. The epic is simply the sum of its dependent parts being fulfilled. Finally, Epic 2, send and request money flow, is explicitly blocked until Epic 1 is complete. You cannot let someone send money through an account that is not yet fully linked and verified. The sequence protects the logical build order. Let's bring this together. Predictive scheduling uses the precedence diagramming method to lock in logical relationships, usually finish to start, into a network diagram that shows exactly which activities must wait for others, like the house building example running from permits all the way to final inspection. Adaptive scheduling respects the same idea of technical dependency, but layers it under backlog priority. Work is pulled from the top of the backlog, and dependency analysis makes sure nothing starts before its true prerequisite is done, as you saw with the Zen tag and bank linking chain. The sequence can still change as priorities shift. That flexibility is the point. In the next part, you will take this house-building network and push it further, calculating the critical path itself and the float on every activity. That's it for this lesson. See you in the next lesson.